What problem does the proposed verbalized machine learning (VML) framework aim to address in machine learning research?
The proposed verbalized machine learning (VML) framework aims to address the problem of interpretability and inductive bias incorporation in machine learning research. VML leverages natural language as the representation of model parameters, allowing for human-interpretable model descriptions and easy incorporation of prior knowledge through text prompts. By using language models as function approximators parameterized by text prompts, VML provides strong interpretability, enables automatic model selection, and allows for detailed explanations of model updates. Additionally, VML treats both data and model parameters as part of the text prompt, similar to the von Neumann architecture, which enhances the framework's problem-solving capabilities. Overall, VML aims to revolutionize traditional machine learning approaches by providing a unified and interpretable framework for model training and decision-making processes.
How does the proposed VML framework work in comparison to traditional numerical machine learning models?
The proposed verbalized machine learning (VML) framework works by parameterizing machine learning models with natural language, where the model parameters are represented as text prompts that are human-interpretable and can encode prior knowledge and inductive bias. In contrast to traditional numerical machine learning models, where models are trained in a numerical and continuous parameter space, stored as numbers, and remain as black boxes, VML uses language models as function approximators parameterized by their text prompts. This allows for interpretability, easy tracing of model failures, and the incorporation of inductive bias through natural language during training. VML treats both data and model parameters as part of the text prompt, providing a unified token-based representation, while numerical machine learning differentiates between data and model parameters. Additionally, VML enables automatic model selection, detailed explanations of model updates, and direct interaction with the optimizer language model. The VML framework offers a unique approach to machine learning by leveraging natural language as the representation of model parameters, enhancing interpretability, knowledge discovery, and problem-solving capabilities.
What are the advantages of using natural language as the model parameter space in VML?
The advantages of using natural language as the model parameter space in verbalized machine learning (VML) are as follows. 1. Easy incorporation of prior knowledge. Natural language allows for the easy inclusion of prior knowledge and inductive bias into the model training process. This enables users to encode their understanding of the problem directly into the model parameters, enhancing interpretability and performance. 2. Interpretability and transparency. The model parameters in VML are fully interpretable as they are represented in human-interpretable natural language. This transparency allows for easy observation and understanding of the model's decisions and updates during training. 3. Knowledge discovery. The model parameters in VML typically describe the underlying patterns discovered from the training data in a language-based form. This property enables VML to uncover novel knowledge that is understandable and learnable by humans, leading to insightful discoveries. 4. Flexible model training. By utilizing natural language as the model parameter space, VML provides a flexible framework for encoding complex inductive bias. This flexibility allows for the easy adaptation of different types of biases and knowledge representations into the model. 5. Improved performance. The empirical evidence supports the claim that using natural language as the model parameters leads to promising results in terms of model performance. The language-based representation enhances the model's ability to capture and learn from the data effectively. 6. Unified representation. VML offers a unified token-level representation of both data and model parameters, unlike numerical machine learning, which treats them differently. This unified representation simplifies the model training process, and enhances the overall performance of the system. 7. Enhanced learning and generalization. The interpretability and transparency provided by natural language model parameters in VML contribute to improved learning and generalization capabilities. The models can be validated by domain experts, and their predictions are grounded in verbalized reasoning. 8. Effective encoding of information. Natural language allows for the effective encoding of information about the problem and desired patterns into the model parameters. This encoding facilitates better understanding and utilization of the data patterns for model training and decision-making. 9. Human-interpretable updates. During training, the updates to the model parameters are human-interpretable, allowing users to observe and understand the changes being made to the model. This transparency enhances trust and confidence in the model's behavior. 10. Improved model adaptation. The use of natural language as the model parameter space enables VML to adapt and evolve the model based on new information and insights gained during training. This adaptability leads to better model performance and decision-making capabilities.
How is the optimization of model parameters handled in the VML framework?
In the VML framework, the optimization of model parameters is handled by viewing the model parameters as a text prompt. The optimization process involves updating the model's language characterization by adding or modifying the model's prior information. The gradient of the regression objective function is computed with respect to the data and the current model parameters. The next step model parameters are approximated using another pre-trained language model, denoted as the optimizer LLM, which takes into account the current model parameters, the data, and the loss function. The optimizer LLM iteratively updates the learner LLM to reach the training objective. The optimizer LLM plays a crucial role in selecting a suitable model class based on the training data and verbalized prior knowledge, providing detailed explanations for each update and allowing for direct interaction to inject new prior knowledge or obtain detailed reasoning. The VML framework benefits from the strong instruction following ability of LLMs, which enhances the performance of the iterative optimization process.
What are the specific outcomes achieved in the empirical studies conducted for VML?
The specific outcomes achieved in the empirical studies conducted for VML include the successful application of VML in classical machine learning tasks, such as linear regression, polynomial regression, sinusoidal regression, two-blobs classification, and two-circles classification. In the linear regression task, VML was able to iteratively update the model parameters to accurately capture the linear relationship between input and output data. In the polynomial regression task, VML demonstrated the ability to adapt from a linear model to a quadratic model to better fit the nonlinear data pattern. For the sinusoidal regression task, VML showed improved performance when prior knowledge about the periodic nature of the data was incorporated. In the two-blobs classification task, VML effectively learned a decision boundary to separate the two classes. Lastly, in the two-circles classification task, VML successfully learned a decision boundary in the form of a circle when prior information was provided, showcasing the capability of VML to encode inductive bias. These empirical studies validate the effectiveness of VML in solving various machine learning tasks and highlight its interpretability and adaptability based on the input text prompts.
What are the limitations identified in the VML framework, and how are they addressed in the future work suggestions?
The limitations identified in the VML framework include a relatively large variance in training due to stochasticity from LLM inference and prompt design, output numerical errors in LLMs, leading to fitting errors, and constraints on input data dimensionality and batch size imposed by the context window of LLMs. To address these limitations in future work suggestions, improvements can be made by enhancing various aspects of VML, using insights and concepts from classical machine learning. Specifically, efforts can be directed towards reducing variance by refining the prompt design of the optimizer and mitigating stochasticity in LLM inference. Additionally, addressing the output numerical errors in LLMs may involve developing techniques to enhance numerical understanding within LLMs. Furthermore, overcoming constraints on input data dimensionality and batch size could be achieved by exploring methods to process high-dimensional data and optimize with larger batch sizes within the limitations of LLMs.